Welcome to Machine Translation. Have you ever wondered how computers can translate Chinese into English? This series of videos explains in detail the methods that underpin today's machine translation systems. So what is this exactly? These videos were prepared for a class on machine translation taught at Johns Hopkins University in the fall of 2020. There's also a class website at mtclass.org/JHU, where you can find additional material, such as the slides for this and the following presentations. So why might you be interested in taking this class? We're going to take a fairly close look at one problem in artificial intelligence. So how can we replicate a skill that we usually would assume requires human intelligence in a machine? It's also a practical introduction to natural language processing. Natural language processing deals with the general problem of how can we get computers to process language just like we as humans do. That's a very exciting field at the moment. There are new applications coming out. The idea of talking to your computer seems to be becoming a reality these days. And finally, it's also an introduction to deep learning. So the current methods that are successfully applied to machine translation also rely on neural networks or deep learning methods. And we're here dealing with a actually fairly complex problem in deep learning, which is called structured prediction, where you can't just, predict a class, say this image contains a cat, yes, no. It is actually, you have to actually create a sentence. You have to actually create a structure. You have to produce a sequence of words. There are two textbooks that we will rely on this class. The one is called Statistical Machine Translation that was published in 2010. And the early lectures, we will mostly draw on that one. It introduces methods that explain how statistics can actually be used to learn knowledge that is required for translation in a more intuitive way. We're actually going to explicitly be able to look at translation tables, and we can actually reconstruct how all the numbers get multiplied up and added up to produce scores for possible translations. And the second textbook that came out this summer in summer 2020 is called Neural Machine Translation, which we rely on. And the later part of the course is explaining the current state-of-the-art methods. So the introductory lecture today will introduce kind of the problem of machine translation in fairly broad strokes. We're first going to start with some history into the problem, the kind of method that evolved over time that we applied to machine translation. We'll give you some sense of where the state of the art is, at least give you some examples, and also explain why translation is a hard problem, but then also give you some evidence how statistics can be useful to answer the problems that need to be solved in when you actually carry out translation. So this is today's lecture is a fairly nice overview about what we will encounter over the course of this class. Let's start with history. So history, we usually start with this quote from Warren Weaver. Warren Weaver was one of the early computer scientists, if you want to call them that way, that were the first people who actually were able to touch computers and do something with computers. And the very early application, since computers emerged during World War II, was code breaking. So the foreign armies encoded their messages in deliberate codes, and breaking these codes is a real important problem for um, winning the war, finding out what the enemy is doing. So after the war, the same people looked at the problem of translation, saying, "Hey, this is actually quite a similar problem." The exact quote is, "When I look at an article in Russian, I say, this is really written in English, but it has been coded in some strange symbols. I will now proceed to decode." So you see some of the jargon that is being used here, decoding, is actually still around today. Up to today, we're going to call the actual inference algorithm that translates a sentence, a decoder. We also call in the neural models one of the key components of the model, the decoder, opposed to the encoder. And so this is still around. So, but some of the very basic ideas were introduced back then. There were actually quite excited research efforts in the 1950s and 1960s. Remember, this is where, as you can see in the picture, where computers were not something that you can carry around with you. Your cell phone is a million times more powerful than what you see in that picture here. But people were still ambitious enough to tackle problems like machine translation. There's a famous experiment in Georgetown at Johns Hopkins University in Washington, where they got a lot of press out of a machine that could translate. It really only could translate 250 words and also only had 6 grammar rules. It was not really a full-fledged translation system that was really useful for anything. And a lot of this excited research that happened then came to a standstill when the government, after spending millions of dollars of research money on machine translation, took a hard look at it and said, is this really necessary? And in this famous Alpaca report, they came to the conclusion there's not really any point in doing machine translation, since we're only spending $20 million back then on translation in the US per year. And all these expensive computers are just not going to make it any cheaper. Nevertheless, people kept working on it. It's an exciting problem. And the first thing that people came up with that actually came to some results and worked were so-called rule-based systems. So the rule-based system is the idea that you just write down all the rules you need to translate. So you have to build obviously dictionaries, but its translation is more than word mapping. You also have to look at transformation rules, and then you have some basic thing in place that can maybe translate some sentence, and you come across some other constructions that are not as suitable for your machine translation system. So you're going to refine and refine and refine. So on the right, you see an illustration of maybe the kind of rules you have to deal with. So if you have to translate a word like have, which is a very ambiguous word, there might be various different ways how to translate that into a foreign language. And it might depend on properties, like if the subject is animate or inanimate, or what kind of other properties the object might have. Um, the earliest successful machine translation system that was actually employed was the Mateo system that was used for weather forecasts in 1976. But also Systran, a machine translation company that's still around, started in that period. And they built a pretty successful machine translation system that was commercially successful in the 80s. There were other systems in the 1980s that were basically rule-based systems that were commercially being sold. So already in the 80s, you could, for your Windows PC, you could download or buy, well, not download, you could buy a box with a CD of Systran, and then you could run Systran machine translation system on your desktop computer. In the 1980s, also another trend emerged, which was the use of statistical methods to solve problems in language. In the 1980s at IBM, there was a group of researchers that first tackled the problem of speech recognition with statistical methods. So the idea was, let's just collect a bunch of recordings of audio, transcribe them and saying, in this second, this word is being said, and that second, that word is being said. We have a very close transcription of that audio, and then try to use methods in signal processing to map from the audio to the text. This is still also a very strong research field. Um, the early work in speech recognition also influenced a lot of what's happening in machine translation. And one fun fact is that the leading researcher at IBM, Fred Jelinek, then went to Johns Hopkins University and was a professor here for many years until he passed away a few years ago. So this group of researchers at IBM then also said, hey, we kind of making progress with speech recognition. Why don't we also do machine translation? And they proposed statistical machine translation. We will actually go into some detail about the kind of models they proposed in this class. In the 1990s, this idea was being slowly picked up. The whole field of natural language processing during that time kind of went through a revolution from the kind of rule-based approaches to statistical approaches. But it really took until around 2000, early 2000s, where statistical machine translation system really supplanted the previous existing rule-based systems. So that was a time of great debate about statistical MT and rule-based MT and what can you trust and how does it work and so on and so on. That was also the time when Google started a statistical system for the online translator, the now uh, uh, constantly being used Google Translate. Um, there was also an open source system that I was leading the development for called Moses that was used widely in academia and also in the commercial world. And I'm saying here on the slide in 2010, there was commercial viability. There was definitely a market for selling machine translation systems. Machine translation systems became a real useful tool also for translators to use in their work. So in the late 2000s, neural methods were slowly being used for computer vision. So neural networks have been around for a long time, and the book actually goes into some detail about this, how long this is really the third wave of neural methods. The first one was in the 1960s, another one was in the 1980s, 1990s, and now we are the third wave of neural methods where really complex are being addressed with neural models. The very first one that really made breakthrough stunning results was neural methods applied to computer vision. So I give you an image, you have to say, is there a dog or a cat? Since about the mid 2010s, neural models were also integrated into machine translation, starting with neural language models as a component of statistical machine translation systems, but then also more complex components. And then in a relatively short period of time, the whole entire field of machine translation sw switched to a completely end-to-end neural machine translation system. So I'm saying here 2016 was probably one of the years that really signaled a break from the previous statistical approaches that actually still relied on statistical distributions collected from counts over data to these deep learning methods. And since then, it's considered the state of the art, and all the kind of big commercial applications of machine translation you're going to encounter in your life will be probably running some version of neural machine translation. Here's a mock-up chart I made a while ago, and that is kind of in the back of the mind of a lot of seasoned machine translation researchers, which is machine translation is both a seemingly simple and seemingly very complicated problem, and there's always people who underestimate it and people who overestimate it. There are always people who say, "Oh, we're going to solve the problem in 5 years," and there are always people who say that you shouldn't even try. This is useless. It's never going to be any useful. So there's been huge discrepancy between what the hype about machine translation is and what the reality is. Um, I already mentioned the Georgetown experiment where they made great claims about we now have an electronic brain that can translate, well, yeah, sort of 250 words. And then the LPAC report bringing that to a crashing halt. Then in the 1980s, where it picked up again, there was a lot of hype about AI in that time too, in general. But slowly but surely over the years, the reality kind of crept up and machine translation became more and more useful. So we're definitely at the time today where machine translation is here. It's widely used. People find it very useful for many, many applications. So it's gotten really good. But we're also at the time where deep learning is horribly overhyped, and people have made claims like human parity, that machine translation is almost as good as human translators. So how good is really machine translation? So I'm just going to give you two examples of actual machine translation output um, in that reflect the quality of today's system. Um, so the first one is translation from Chinese. I actually ran this through a system already a couple of years ago, so maybe it has improved. But if you do not know Chinese, this looks like a bunch of gibberish, although it has some numbers in there that you can read, but the rest of it is fairly meaningless. So um, if you want to make claims about human performance of translation, I don't know what that means at all. So machine is probably better than me. But if I would know Chinese, then I would probably do better than the machine. So here's what a machine translation system produced for that. Reporters learned from the Ministry of Environmental Protection Water 10 requirements before the end of this year, before the municipality, the provincial capital settled plans to build a separate city to solve the basic black and black water. Up to now, the country's 224 prefecture level and above cities were identified to confirm the black and white water 2082, of which 34.9% to complete the renovation, 28.4% is remediation, 2.8% is carrying out the project early. So this is obviously some unclear, badly mangled text, but it's clearly also text about water treatment plans, about some kind of assessment of project status of water treatment projects, how many have been done and how many have to be doing. So we kind of know what the subject matter is. It's very hard to say what exactly the details are. Like it's not entirely clear what the percentages really refer to. Maybe it means that the first one is highly suggests that 35% of the projects are completed, but others seem to be in various stages. But this 2082 is completely unclear. So that's a translation from Chinese. I'll give you another example. This is a machine translation from French. So here the translation reads as, at the beginning of this televised debate, which was unheard of in the history of the Fifth Republic, a two-solo Macron was expected, but it was the candidate of the National Front who found itself at the heart of the first attacks of its four opponents of one evening, favored by the first theme tackled, the issue of society and thus security, immigration, and secularism. So this reads actually pretty nicely. Um, there's some debate if this Tous Macron should have been translated as all against Macron. Probably should have, because it's not quite clear what it means, and it's not really a name of anything that you want to preserve the name of. There's a very striking error of the candidate of the National Front who found itself. I mean, you wouldn't refer to a person as it. And in fact, this person here is a woman, so you would say herself. So it got that wrong. But otherwise, it's a pretty impressive translation. So this is pretty good. I showed you two examples. Chinese has long been considered a very hard language to translate. It's just much distant from English. There's not much shared vocabulary. And French being a very closely related language. Actually, if you just stare at the French without knowing anything about the French, you're going to see words like candidate and national um, that you can actually understand as an English speaker. So how can you build machines that can do these kind of translations that we just saw? So let me first come up with one angle at attacking this problem. So this is a plan that's been around for a long time and thought to be the way to build machine translation systems. So we could just come up with a sentence in the source sentence language and map it by just translating all the words into the target language. Maybe we need to have some fancy rules about reordering, but the idea is it's just pretty much a word mapping problem, and that's what we should focus our attention to. But maybe that's not enough. Maybe you should actually do some linguistic analysis. So this means detecting what is a noun, what is a verb, what is a clause, where's the subject of a sentence, where's the object of a sentence. There might be fairly principled ways how to map syntactic structures between languages if you know what they are, so the transfer stage becomes shorter. But syntactic transfer still operates on fairly surface level visible parts of a sentence. What we really want to translate is the meaning. So if we process the source sentence through some kind of analysis into a meaning representation, then the transfer stage becomes even closer. You just have to map from a source language meaning representation to a target language meaning representation. And ultimately, the goal is to do interlingua translation. So if you have a meaning representation that is true beyond all languages and can be used for all languages, then you don't have to do any transfer anymore. You just do an analysis into that interlingua representation, and then from that interlingua representation, you generate the target output. So this graph that I'm showing here, it's also called the Vauquois triangle, has been very influential in driving motivation how to build machine translation system for quite a while. The other big idea is to learn from data. So the idea is that you have training data on one hand, uh, parallel corpora, so translated text, monolingual corpora, these are just any text in the languages involved, dictionaries, and maybe also linguistic tools, and that allows you to kind of collect the statistics to build a machine translation system. And then at runtime, when you actually want to use it, you just take the source text, run it through the statistical machine translation system, and produce a translation. So the key here is you learn from data. So why is that a good plan? Let's first look at some of the problems that we will encounter during translation. We'll start with word translation problems. Words are ambiguous. So the classic examples here are the word interest and the word bank. These have starkly different meanings in these sentences. So the first sentence, he deposited money in a bank account with a high interest rate. You have bank here as a financial institution and interest rate as, the fee that's being paid for a loan. And the other sentence is sitting on the bank of the Mississippi, a passing ship piqued his interest, where bank here is the shore of a river, which has nothing to do with a financial institution. And the interest here also has no financial meaning. It just means a sense of curiosity. These are very different meanings. And in many languages, they might have very different translations. So if I translate this into Chinese, into German, I might actually have to pick different words for their translations. So how is a computer going to figure out that bank in the first sentence is different from bank in the second sentence? Well, how do you know that bank in the first sentence is different from bank in the second sentence? You know it because you just look at the surrounding words, and from the context, it's pretty clear what the meaning of these words are. And that context is also available to a computer, and somehow that context should also help a computer to translate. Here is an example for a syntactic translation problem. This is a very short sentence, still pretty tricky to translate. So the German sentence is, das behaupten Sie wenigstens. And das means either this or the. Behaupten means claim as a verb. Sie is either they or she. And wenigstens means at least. And you actually have to convert here from a sentence order that starts with the object, then the verb, and then the subject into a sentence that has subject, verb, object order. So the translation should be something like, they claim this at least, or at least they claim this. So there's a bunch of ambiguities that have to be resolved through syntactic analysis. So if you look at the word das, the very first word, so the translation the is not really probable because there is no noun following it. So it's not really part of a noun phrase. So it really should be than the word this. And then there's this question if sie here means they or she, and it's not going to be apparent for someone who doesn't understand German, but if you look at the word behaupten, you know that this is in plural, so the right translation has to be the right meaning of the word sie is the meaning of the word they and not she. So all this has to happen. So there's a lot of structural syntactic ambiguity that recognizing that this is an object verb subject construction instead of a subject verb object construction. And this mostly follows from morphological agreement and the plausibility of different possible analyses. Here's a semantic translation problem. So pronominal anaphora, so pronouns and what they refer to. I saw the movie and it is good. So this is not a hard sentence to translate, probably in many languages. One key problem though is what to do with the word it. So it here is neutral, but it refers to movie, and movie in many languages uh, has a translation that is a gendered noun. If you translate it into German or French, nouns are not just all neutral if they're not actual persons as they are in English, but they might have gender. And in this case, in German, if you translate movie into film, film is masculine gender. So then the it has to be translated into the masculine pronoun er, so the equivalent of he. And this is something that's really tricky to do. Here's another semantic translation problem. So this is a somewhat made up example. It's somewhat an argument while to do machine translation really well eventually, you have to solve all the hard problems in artificial intelligence that have to do with world knowledge. So here's a sentence. When I visit my uncle and his daughters, I can't decide who is my favorite cousin. And how do you translate cousin into German? In German, there's no gender neutral word for cousin. You either say it's a male cousin or female cousin. Just like in English, you usually refer to your brother and your sister, and nobody really uses the word sibling, which would be gender neutral. You don't really talk about, I met my sibling today. That's just an odd thing to say. And German doesn't even, in this case, your German doesn't even have a gender neutral word for cousin. It's always gendered. So what gender is my cousin here? Well, I'm talking about the daughters of my uncle, so they're female cousins. So this requires fairly complex inference. You need to know something about family relationships and so on. And how is the machine going to acquire that kind of knowledge? That is a really, really hard problem. Here's another semantic translation problem that has to do with discourse. So now we're going beyond like what happens in simple sentences. Be looking at the relationship between sentences. So here two clauses. Since you brought it up, I do not agree with you. So the since here is more like a, because you brought it up, I want to point out I don't agree with you. Versus the second one, since you brought it up, we have been working on it, which is more like since back in the days when you brought it up, we have been working on this problem. So since it's more like a temporal since the time you brought it up. So in the first time you can replace it with because, and the second time you can't, and the word might have different translations. And what translation to choose really comes out of the analysis of the discourse structure. Again, a hard problem. So what can help us to make these decisions that we have to make to resolve these ambiguities? Well, so here's the idea. We're going to learn from data. So if you look up it in a dictionary, you might come across the word Sicherheit, a German word that has, according to the dictionary, three different translations: security, safety, and certainty. And I mean, even as English speaking speakers, we can probably appreciate that security and safety are kind of closely related. It's not quite clear actually what the difference is between security and safety. And then there's the word certainty, which is kind of in that realm. So it's not as stark as a contrast between, let's say, the different senses of bank or the different senses of interest, but there's still at some points one word is appropriate and then other time another word is appropriate. So here are the counts how often a word has been translated in different ways in a corpus of texts from the European Parliament. So there we can see the word Sicherheit was translated 14,000 times as security and 10,000 times as safety and relatively rarely as certainty. So just based on these statistics, we would say if we don't know anything else, we should probably go with security, and then we are most of the time right. Not always, but we're gonna be more often right than going with the other word choices. So this is the most easiest way to apply these statistics. If you actually look at the surrounding words, it helps a lot to disambiguate the meaning. So here, the word Sicherheit is paired with another word. In German, this is now written together. German has these famous noun compounds, but it's essentially really just a sequence of two nouns. So you have Sicherheitspolitik, that means security policy. That is 1,580 times and rarely is translated as safety policy, and certainty policy doesn't seem to exist as a concept. If you look at another word like Lebensmittelsicherheit, that seems to be food safety, rarely as translated as food security. Food security actually exists as a concept. It actually means something else. Food safety is your food safe to eat? Food security means do people have enough food to eat? And then you have Rechtssicherheit, and this is where the meaning of certainty actually comes up as the most prominent. Rechtssicherheit means legal certainty. Rechtssicherheit means can you rely on the laws being the way they are, and you can trust that this action you're going to carry out is actually not going to be legally challenged. So legal security also occurs in the corpus, and legal safety, but much rarer than legal certainty. So here, the surrounding words help you to disambiguate how to translate an ambiguous word. So we also have to produce text in the target language, and we want to produce fluent text. And what is the most fluent text? So is it a problem for translation, a problem of translation, a problem in translation? What is actually, if we don't know how to translate a pronoun, we need to put a pronoun in there that somewhat clarifies the relationship between problem and translation. What should you do? And again, we can just look at which phrase is more frequently used. And apparently, a problem in translation is being used more frequently as a problem for translation or a problem of translation. This is based on just hits on Google, how often these phrases occur on web pages indexed by Google. Actually, the most frequent one is a translation problem. So it's a different way to get away without having this pronoun preposition in the middle. That is vastly more frequent than anything else. Here's another example. I'll let you guess a little bit which one is the best way to phrase this. The police disrupted the demonstration. The police broke up the demonstration. Police dispersed the demonstration. Police ended the demonstration. Police dissolved the demonstration. Police stopped the demonstration. Police suppressed the demonstration. Police shut down the demonstration. These seem to be all roughly fine ways to say this, but if you had to force to choose one of them, what is kind of the most common way to express the meaning here? According to the word counts, it's the police stopped the demonstration. Interesting, stopping something and ending something seems to be really, really similar, but if you look at the counts there, they're dramatically different. Okay, so where are we now? Let me just go over some of the methods that have been proposed, some of the big architectures that have been proposed to address machine translation. So the first method that seems to be very useful is you have to tackle the problem of word alignment. So when you have a sentence pair here, the English sentence is Michael assumes that he will stay in the house, and the German sentence is Michael geht davon aus, dass er im Haus bleibt. Which word actually refer to which other word? So you need to figure out that Michael and Michael are translations of each other. Because the data we're going to get are sentence pairs. So this is the best we can hope for, that we're going to find text and we somehow manage to align sentences. And then we know here's a for English sentence, here's a German sentence. But nobody is going to then tell us more than that. Nobody's going to annotate for us which words translate to which other words. That's just a hugely time-intensive thing, and it cannot really be done on scale. So this is the one problem we have to solve. With that in mind, for a long time, the dominant model in machine translation was the so-called phrase-based model that says, well, it's not translation doesn't always involve the translation of single words. Maybe translating of multiple words at the same time is useful. So this might be that a word like natürlich actually has two-word translation, of course. But it also is that surrounding context helps ambiguate. So here Spaß am, fun with the. So um, the translation of this very ambiguous as with the from the is probably driven a lot by the preceding noun that the preposition is attached to. And it's going to help with translation. So when we don't learn translation rules over whole phrases instead of words. I showed you earlier the examples with Sicherheit and security and safety, and learning the phrase translations actually going to be much clearer than learning word translations. So this is actually in one slide pretty much the key fact about how phrase-based models work. So you take a source sentence, split it up into phrases in arbitrary ways, really, and map each phrase into the foreign language and maybe reorder the phrases. So this is the workhorse of today's statistical machine translation method, although they have been obviously supplanted more recently by neural methods. Here is syntax-based translation, so the later stages of statistical machine translation. People try to build models that follow this quad triangle upwards. So how can we first carry out syntactic analysis and then have mapping rules that operate on syntactic structures? So here I have a German sentence. Sie will eine Tasse Kaffee trinken, which if you just translate it word by word means she wants a cup coffee drink. And the really tricky one here is, of course, the wants blah, blah, blah drink, where the verb is at the end of a sentence and has to be reordered. And this is captured in this rule here, where it says, if you say wants to, and then there has to be a verb and a noun, these actually get reordered. So here, these lines here then cross. So the verb gets attached right after the to, while the noun phrase gets attached at the end. There have been also efforts on semantic translation. So this is ongoing work, and it's pretty much wiped out by more recent work on neural machine translation. Although let's keep that in mind. Maybe that's one solution to make the models a bit more sophisticated in the future. So the idea was, let's go beyond syntax. Let's actually come up with meaning representations. And here is one particular meaning representation. It's called abstract meaning representation. So this particular sentence here, it's about a wanting action. So the key part of a sentence is always the verb. That is kind of the core element of a sentence, that what ties the sentence together. This wanting requires an agent, so someone is doing the wanting, and then an object, which in semantic jargon is often called theme. So here the object is actually another verb. So what the boy wants is an action, and what the action is a love action. So he wants some love action, and that also has a person and an agent. So who is doing the loving is the girl, and who is here the object, now called patient, is the boy. So the B here is the same B as it's up here. So the boy occurs twice in this meaning representation. One is actually explicitly explained what it is, it's boy, and later it's just referred to as a variable. So what this sentence supposedly means is the boy wants the girl to love him. And that's the meaning representation. So the nice thing about this, it generalizes over equivalent syntactic constructs like active and passive sentence. It also very clearly spells out semantic relationships. And the idea is that if you have a meaning representation for English, it shouldn't be too hard to take from that and map for that into a meaning representation for, let's say, Chinese or German or French. And so the mapping step, the transfer step becomes much easier. Okay, so this is what's happened uh, in more recent years. These are neural models, and hopefully this doesn't shock you too much. We're going to slowly approach these neural models in our later lectures. Um, let's just look at some of the elements in there. So the key here is we now draw this bottom up. So there is an input sentence. So we have the input words here lined up, and first have so-called embeddings for them. These get processed, so there's some encoding going on, and then there's some decoding later, um, and you predict output words from that. So this is one very particular model architecture that are underlying neural models. I'm just gonna leave this here and not gonna explain it much further. We'll go into great detail how neural models work. So let me conclude the lecture with kind of the question, what is it? Why are we even doing this? What is machine translation good for? And the real question is, what is it good enough for? So the question is not, I think it's always a bad question to ask, like, how good is machine translation? Is it good enough? Is it perfect? And the real answer is it good enough for something? What applications do you have in mind? What kind of quality barrier do you need to have to answer it? We earlier saw two examples of kind of news text, one in Chinese, one in French, that were translated. The first one, yes, it was fairly gibberish translation, but you kind of knew the general topic. So if you're just interested in, like, can I find articles about this particular subject matter, the translation was actually good enough for. So this might be relevant for a patent lawyer that tries to find similar patents to the one that's being filed. And he just needs to know, is this also in the same area? It doesn't need exactly the details how the method that is proposed in the patent works. It just needs to know roughly is in the same area. Okay, let me just kind of break down the kind of big tasks of machine translation. So one has a fancy name called assimilation. So this is the idea that a reader initiates this translation process and wants to know the content. So this is you going to Google Translate and giving it a web page to translate and then producing the translation. So the user is somewhat tolerant in this case of inferior quality. You know that you're operating with machine translation. You don't expect perfection. You just want to get some kind of utility out of it. You want to gather some information. So this is the focus of a lot of the research that has happened in recent years. Another application is communication, where the participants don't speak the same language and they rely on translation. And they're very obviously aware that what they're saying is being machine translated. So again, there has some tolerance for error. If things come across, they hopefully then come up with follow-up questions and don't get horribly insulted when the translation is off. So this has been applied to chat room translation, and there's always this hope of like a handheld device. You can travel to a foreign country and just with a handheld device, you get around and talk to people that only speak the local language and not your languages. So it's often combined with speech recognition. And there's been even a big evaluation campaign on at the International Workshop on Spoken Language Translation that tries to push this kind of speech translation as a problem. And finally, there is dissemination. So this is kind of the commercially biggest application of machine translation. You're a publisher, you want to make content available in other languages, may it be because you're selling products abroad and you have to explain how your refrigerator works to people in Estonia, and you obviously can't just give them the English manual. They're going to be annoyed with that. They want to have the Estonian manual. Uh, but it's also things like, nowadays Netflix tries to localize their TV shows and the subtitles have to be translated into many, many languages. So the publisher here wants to make this content available, and there's a pretty high demand for quality. So the recipient of the translation really expects, fluent text that they can read without any problems. So this is currently almost exclusively done by human translators in some way. Obviously, machine translation can also help human translators, and we'll have a whole lecture at the end of the course where we talk about computer-aided translation. How do you help human translators? So one big problem in machine translation, and we're going to have a long discussion about evaluation in one of the future lectures, is it's actually not a perfectly defined task. So there's no single right answer. So this is actual data from an actual corpus of multiply translated Chinese text. This was prepared about 20 years ago in the early days where the big challenge was, can we translate Chinese into English with statistical methods? And to check the quality of the translation, we'll say, let's just compare to a human translation, and let's not just take one human translation, take multiple human translations. So all the sentences were then translated by 10 different translation agencies, and they came up with these different translations. And if you read through them, Israeli officials are responsible for airport security. Israel is in charge of the security of this airport. The security work for this airport is the responsibility of the Israel government. Israel's side was in charge of security of this airport, and so on and so on. So you kind of go through it, and they kind of mean pretty much the same thing. Um, any of these translations can probably be criticized, and some of you might prefer some others more than others. It's kind of famous among translators that they never really like other people translators and other people's translations. So there's in this argument what is right, and if you really nail it down, you can even make the claim that all of them are wrong. There's some kind of nuance in that Chinese title that's always going to get lost during translation. But what it is striking that these 10 different translation agencies came up with 10 different translations. And it's not unusual. This is the standard. Any kind of reasonable length sentence, and this is not even a long sentence here at all. If you give it to two different translators, they will come up with two different translations. Okay, one last word on quality to wrap up this lecture is we would like to get a bit more clearer sense of quality, like how good is machine translation. And here's a scale that was proposed by a DARPA program on machine translation and related natural language processing problems, where they introduced something called HTR, which was the human annotated translation editor rate. So what happened here? The machine produced a translation, and then a human had to fix it up to make it correct. And then we counted how many words were replaced or reordered. And each edit step counted as a mistake, and then divide then the edit steps by the length of the sentence, and that gives you the edit rate. And then they came up with a scale by saying, well, if it's 5% edit rate, so only 5% was edited, according to this definition of editing, it's publishable. If 15% it's editable, it means it's good enough that you're going to be faster editing the machine translation output than translating it from scratch. And at lower areas, it's gistable, meaning you kind of understand the meaning of it in at least broad strokes, maybe even if some details are lost. And the last one is triageable, which is really just, can you figure out what kind of roughly is this text about? The triage here is it something that interests me, or is it something that doesn't interest me? If it's something that interests me, then I can maybe give it to a human translator for further assessment. So here's maybe some applications that tie up with these levels of quality. So if you have 0% human edit rate, then you really seamlessly bridge the language divide. You actually solve the problem. But if you only have 5%, means you can maybe automatically publish official announcements or help pages or stuff that people gonna be not super picky that everything is perfect, but it's gonna be, very clear in all details. Another threshold is obviously editable. So does it increase the productivity of human translators? So if human translators, by editing machine translation output, are faster than translating from scratch, that's an important translation quality barrier for machine translation. And so on and so on. So further down, we're going to have here, for instance, information gathering, identifying relevant documents. So there's different quality barriers, maybe also for multilingual communication, chats, and so on. The threshold is not as high. You just basically want to know what did he say and not really need to have all the nuance and details perfect. So this is the current state of the art. Again, this is completely made up. I'm just giving you some sense of where we are. So I would say for restricted domain French English, you can probably do zero error translations. I think if you would collect a large corpus of weather forecasts where they actually stick to the weather and don't give you any vacation advice or other anecdotes, it probably can do pretty perfect with that. I already showed you a French English news story. So these are also pretty good. French, if you just try it out, go to a French newspaper website and then run things to Google Translate. You'll find these stories extremely readable. There are tougher languages like German and Chinese where that's not necessarily the case. And then there are languages where, mostly because we don't have that much data, we're actually going to do much worse. So Swahili, we don't have much data. And then there's really Uyghur, which is a minority language in China, where we have very, very little data and we're just not going to get much done. So a lot of the action nowadays is actually in this space here now. How do you build machine translation, not just for the top leading languages where we have lots and lots of data and actually doing good enough for most purposes, but how we do for languages where we don't have many resources. Okay, and that's it for today. If you have any questions, post them in the comments, or if you're actually taking the class right now at Johns Hopkins, come to the lecture on Tuesday. Thank you.